Okay, can I go?
Yeah.
Excellent. Good evening. My name is Dr. Adi Patterson. I'm the CEO at ANSTO.
With you on the screen here.
I'd like to welcome you to Quest for Quantum. It's my pleasure to be your host for this evening's event. We're going to be discussing the latest developments in quantum mechanics and the potential applications in exciting opportunities for Australia in this brand new industry. As we begin, I would like to acknowledge the traditional owners of country throughout Australia and recognise their continuing connection with the land, the waters and culture, and I pay my respects to their elders past, present and emerging. Quantum mechanics. This is the cutting edge. I grew up in the classical world. We are now going to live in the quantum world, the world where we use the quantum power of the atom to do cutting edge science and to push what we know about the quantum science itself, but also make devices like computers using the quantum. To do this, we are moving from transistors like we used to know them into really new types of devices that will work very differently. And the panel that we've assembled tonight is going to be sharing their knowledge of these fields and all of the important transitions we're going to go through. People estimate that this industry in the future might be worth $86 billion by 2040. It's an industry in which Australia is making breakthroughs, is leading the innovation and the development of new technologies. And we have the opportunity tonight to hear from an amazing panel. 2018 Australian of the Year, Professor Michelle Simmons from the University of New South Wales, the CSIRO Chief Scientist, Dr. Kathy Foley, who recently received the Order of Australia, and ANSTO physicist and Honorary Secretary of the Australian Institute of Physics, Dr. Kirralie Rule. Thank you to all of our speakers for being here tonight and being involved. Each speaker is going to make a short presentation this evening, and there'll be plenty of opportunities for you to ask questions using the Q&A button on your screen later in the event. The wrap-up will be done by Scott Martin from the Australian Institute of Physics towards the end of the evening. We're going to start with our first speaker tonight, Dr. Kirralie Rule. She is an internationally recognized leader in understanding magnetic materials. And does amazing work here at ANSTO, doing experiments using both the neutron scattering facilities and the synchrotron down in Melbourne, which is a really big light source about the size of a soccer field. And she has worked in a number of research groups around the world, making contributions in the United States, Canada, and Germany. I find that she has always got the best questions in the meetings that I have with her. And she has also recently been elected onto the Executive Committee of Australia's peak physics body in 2017, the Australian Institute of Physics. So she's going to start us off tonight with some insight into how quantum mechanics works. And so I'd like you to welcome her with a virtual clap, because we are not in the room with Kirralie, and to support her as we listen to her explaining quantum phenomena to us. Thanks, Kirralie.
Thanks very much, Adi. And it's a great pleasure to be here tonight. Let me just share my screen. And I will just put it into presentation mode. It's coming. There we go. So I'd like to start off my presentation here just talking a little bit about ANSTO. First of all, we know that ANSTO's Lucas Heights campus is located just south of Sydney, and it's the home to the only operating nuclear reactor that we have in Australia. And in fact, we've been operating nuclear reactors here since the late 1950s. First of all, with the HIFAR reactor, which is the reactor where I did a lot of my PhD work, incidentally, and now since 2006 with the Opal reactor. So ANSTO is a public research organisation, and it employs around 1,200 people, And as Adi mentioned just before, we also have a campus down in Melbourne where we're operating the Australian synchrotron for light source. So the OPAL reactor. OPAL stands for the Open Pool Australian Light Water Reactor. And what you're seeing here on the screen is a zoom through the layers of the swimming pool down in towards the core of the reactor. So this is a really unique view you're getting here. What we can see right in the center of the screen is a square, and this square is around the size of a standard household washing machine. And this is where we contain our uranium fuel, and this is the core of our reactor, where the fission process it undergoes. And what you can see around the core of the reactor is that there's a whole range of different ports and pipes and hoses and tubes, and we use all of these for the different multi-purposes of our reactor. So first of all, as has been mentioned, we produce a lot of medical radioisotopes and radiopharmaceuticals at ANSTO. So this is for the detection and treatment of different cancers. And so a lot of Australians around the country will benefit from the radiopharmaceuticals that we produce here in our reactor. We also provide neutron activation. This is a form of elemental analysis where we can determine down to the parts per billion level what elements are in a particular material. We also perform silicon irradiation. Now, this is where we take really high quality silicon ingots, some of them up to 20 centimeters in diameter, and they undergo a transmutation where we change some of the silicon to phosphorus to improve their conductivity in these silicon ingots. And these are sold to industry and commercially. And finally, the section that I'm involved with at ANSTO is the scientific research that we perform using the neutrons that are forming through the fission process in the core of the reactor. So the neutron instrumentation is operated by the Australian Centre for Neutron Scattering at ANSTO. And as you can see here by the suite of 15 instruments, we like to name our instruments after Australian native animals, with the exception of 2 instruments. And I won't tell you what 2 they are. I'll leave it to those people watching to determine which of the instruments we haven't named after Australian animals. So each of these instruments is unique and has a unique purpose for studying structure and dynamics and different properties of materials. And you can see that they've been separated into different groups, if you like: diffraction, inelastic, reflectometry. So because the OPAL reactor operates for around 300 days a year, this gives us the opportunity to run around 450 unique scientific experiments on these instruments. And our scientists who come to use our facility come from all across Australia and across the world, owing to the world-class nature of the facilities that we have here at ANSTO. So my research is based within the inelastic neutron scattering suite. You can possibly see me here discussing some scientific results with a colleague. Inelastic neutron scattering involves looking at dynamics in materials. So looking at how thermal influences might make atoms vibrate, or looking at how an ion might diffuse through a crystal lattice, or how magnetic moments might fluctuate. So on the right-hand side of the screen here, you can see that I've listed a lot of different properties of neutrons which make them ideal for investigating condensed matter systems. The wavelengths of neutrons pair nicely with atomic spacing, so they're great for looking at atomic structures. The energies are great for looking at different dynamics. What I've shown here on the left is a diagram showing that neutron diffraction, looking at structures in materials, can cover around 5 orders of magnitude. But what you can see is there's a significant overlap with some other techniques that you might also be familiar with. However, neutron scattering is very complementary to all these different techniques. It can often reveal different information to what you might get from X-ray diffraction or electron diffraction. And that comes from the way that the neutron interacts with the nucleus as it's scattering. And so this means that our neutron scattering is going to be strongly interacting, and it's highly penetrating. And we can really use that to our advantage so that we can look at real world problems. So for example, we might look at hairline fractures or failures in the welds of a railway sleeper. Or we might look at a battery that's going through its charge and discharge process, and we can actually see what's happening in that commercial battery during a neutron scattering experiment. But what excites me is having a look at this phase diagram, opening it up to having a look at the energies that we can investigate with inelastic neutron scattering. And you can see here that there's not so much overlap anymore, and that inelastic neutron scattering is really well tuned to investigating dynamics in materials. The property that I think is probably the one that I use the most, or that I appreciate the most, is the magnetic moment of the neutron and being able to investigate magnetic materials. But what does this mean? What does it mean that the neutron has a magnetic moment? It has a magnetic spin. What's going on there? Well, in fact, all of our fundamental particles, the electron, the proton, and the neutron, they have this property called spin. It's a quantum mechanical property, and it's actually intrinsic to the fundamental particle, just like charge is intrinsic or mass is intrinsic. So it's a quantum mechanical concept, if you like, this spin. But what is it actually? Well, we can have another look at it from a classical viewpoint. So if we have a look at a classical viewpoint, let's take a current carrying electrical wire. So if we have a current carrying wire with the current heading down this direction, we know through electromagnetism, the coupling of a current with magnetic field, that we will have magnetic field surrounding this current carrying wire. Now imagine that we can draw this current carrying wire into a loop. That's quite nice. What happens then is we are able to produce magnetic field lines which come out of the center of our current carrying loop. And in fact, what you can probably recognize from this diagram is now it starts to look a little bit like a bar magnet or a dipolar magnet, a magnet that has both a north and a south pole. And you know, you put something like this down with some iron filings and you can certainly see these field lines from a bar magnet or something similar. So now let's take it one step further. What if we were to now make our current carrying loop into an electron that's spinning? So if our electron was spinning, we know, if you did high school physics, we've got the right-hand curl rule, that if the electron is spinning in this direction, we would have a magnetic field perpendicular to this, upwards. And if it was spinning in the opposite direction, we would have a magnetic field downwards. However, this is a nice classical picture of what might be happening if we talk about spin, and probably where the word spin came from. But the truth of the matter is, the electrons aren't actually spinning. And the other point, neutrons are a fundamental particle. They also have this property of magnetic spin, but there's no charge for them. So having this nice classical analog gives us an idea of the concepts we're talking about when we're talking about spin. And spin is a vector quantity. So it has a magnitude and it has a direction, and that direction can point in any way that we like. We can also have a look at electrons and spinning electrons with another analog. For example, here's our electron spinning around our nucleus. We can also compare this to the Earth spinning around the sun. We know that the Earth spins on its own axis and in fact also has a magnetic field. So that's a picture that some people like to keep in their mind of what the electron is doing around the nucleus. So the materials that I look at, or the types of research that I do, is looking at low-dimensional quantum magnets. Now, what on earth is that? What's a low-dimensional quantum magnets? Well, when we look at the atomic structure of these materials, they're three-dimensional structures. They've got a length and a width and a height. You can pick them up in your hand, no problem at all. But what we're doing in these materials is we're restricting the magnetic interactions, or the magnetic ions, to lie within, say, a plane or a chain. And by doing this, we're able to restrict the number of interactions between our magnetic ions. So in this picture here, the chains can't talk to each other. However, each of the neighbors, the next nearest neighbors, can talk to each other. And with neutron scattering, we can isolate these interactions and directly measure what's going on at a very fundamental level in one dimension. Once we move into two-dimensional planes, we start to increase the number of interactions. And by the time we get to 3 dimensions, it becomes quite complicated and very difficult to understand in many respects. And so this is why we try and reduce the dimensionality of our magnetism, so that we can design models and learn of the best ways that we can manipulate materials to get them to do what we want for us. So ways that we can manipulate our magnetic materials to make our spins align for us is we can apply different external stimuli. We can perturb our system. We can either change the temperature, apply a magnetic field or electric current, apply a pressure or even light to change the magnetic properties of these materials. And then we can use neutron scattering to investigate exactly what's changed and to what degree. And so we can, many of these low dimensional magnetic materials can host some quite exotic phases. And it's these exotic phases that hold some keys to technologies in the future. Something like a spin-nematic phase, or even a Bose-Einstein condensate, where you might have magnetic spins with a similar axis that are free to move relative to the lattice. We might have a frustrated lattice where we have competing interactions that prevent long-range order. The spin-liquid lattice, something where we have very strong interactions between neighboring spins, but they just can't sit still. They are continuously dynamic. And then you could have something like a skyrmion lattice. Now, these are great. They're a big vortex of spins that then have a large periodicity in our structures. So what technologies are we talking about? Where can we start to harness this spin and manipulation and control of the magnetic spin for future technologies? Well, an emerging field that's really quite exciting is the field of spintronics. Now, we know what electronics are. Electronics is when we're moving information by pushing an electron through a wire, through a current carrying medium. Now, the problem with moving electrons is they have a mass. It's not a big mass, but it's a mass. So they're quite heavy. It takes time to push them through. They have a lot of resistance. Obviously, there's lots of different research centers who are looking for ways of reducing resistance and improving speed in these electronic circuits. But another way we can do that is now by looking at spins and transmitting information through a medium via the direction, the vector direction of the spin. Now, because the actual atoms don't have to move, we're only moving the vector direction, the direction that our arrows or our magnetic spins are pointing. We can then transmit information a lot faster. And because there's nothing moving, there's no resistance, so they become more efficient. And we can start using materials with transition metal elements in them, and so we can bring down the cost for high fidelity information transport. So what are the technologies? Well, ferromagnetic technologies exist right now, and we're using them in some of our devices right now. So ferromagnetic means that our magnetic ions are going to face in the same direction. They're going to point the same way. And so some of the spintronic ferromagnetic technologies that are available involve memory devices, logic gates, and sensors. So we're using these now, but an emerging area in this spintronic sector is looking at antiferromagnets. And this is really exciting because antiferromagnets now have spins that point in opposite directions. And so what they've been able to show so far is that the speed of transmission of information through an antiferromagnetic spintronic is 3 orders of magnitude faster even than a ferromagnet. So this opens up a really exciting future where we could look at these spintronic devices for transmitting information in artificial neural networks or things of that nature. So with that, I'd like to pass on to Michelle and to Kathy to talk a little bit more about how we can harness some of these quantum ideas for technologies of our future.
Thank you very much, Kiralee. Are we going to do some questions?
Yeah.
Yeah, I got a couple of questions just before we go to the next speakers. One of the things that I learned about magnets when I was doing my physics was that there's this kind of a North Pole and a South Pole. And isn't one of the big goals to try to find a magnet that's only got one pole, just a South Pole and no North Pole? And have you got anything to do with that field and anything you can tell us about it?
Yeah, absolutely. This is an excellent question, Adi. I mean, it's been debated for, nearly 100 years now. I think that it was the British physicist Paul Dirac who was saying that to make Maxwell's equations symmetric, if we can separate electric charge, electrons and protons, separate them to be unique particles, then why can't we do the same with magnets? Why can't we get a bar magnet, snap it in half and have a north and a south? And the reason is, well, whenever you snap a bar magnet, you don't get a north and a south, you get 2 smaller bar magnets, each with their own north and south pole. And if you continue breaking these down, finally you're going to get to the fundamental limit where we know that our fundamental particles have this spin, this property of spin. So what we've been able to do, if I could share my screen once more. I don't know if my screen is still sharing. Is it still sharing?
Other way.
Yeah, here we go. So what we were able to do a little while back, I've got some slides based on this, is instead of separating our north and south poles so that we have a unique north and a unique south that are completely separate, we were able to sort of induce these in a magnetic lattice. And these are always going to be connected by what's called a Dirac string, which is infinitely thin and infinitely long. So the system we were able to do this in was called dysprosium titanate. It's a pyroxyle lattice, which when you squash it down looks like a square lattice, as you can see here. And in this system, the dysprosium is the magnetic ions, and they like to sit on this lattice where they have zero net magnetic moment on the inside of each square. So it's called a spin ice configuration, where we get 2 spins in and 2 spins out of every single square. So the net magnetism is 0. You couldn't hold up your favorite photo on your fridge with this material. It's an antiferromagnet. However, with a little bit of energy, applying a little magnetic field to the system, we're able to flip one of these spins. And therefore, we're able to create a north by 3 in, 1 out, and a south, which is 3 out and 1 in. And we were able to show that the system itself wanted to stay in this spin ice structure, this 2 in, 2 out structure. So what was happening was that our spin and our south pole ended up moving a long way away from our north pole. And this was quite interesting because we could move them far enough away that if we just focused in on this part of the lattice, it almost looked like we were able to create this north pole. So that was quite exciting, but it was trickery. It was a quasi-particle. And I read actually recently, the Large Hadron Collider in CERN is actually really focusing their efforts on looking for real individual particles of magnetic monopoles. They've got a whole device, the modal beamline, the modal device, which is really designed to capture an event of a magnetic monopole. So that's really exciting.
Really, that's amazing. So you are the closest thing to a magnetic monopole on the planet. And I think that's pretty awesome. Now, if you were to say then, will these quantum magnets, we just at the beginning of this journey of really separating out these poles, what would be your favorite new device that you'd make with just a poor old North Pole all by itself?
Oh, that's an excellent question. I haven't thought of this. Yeah, I don't know. I mean, if we look at Maxwell's equations and having things that we can do with an electric charge by itself, and analog straight with a spin.
Yeah.
But these magnetic monopoles are really interesting. They're meant to be extremely massive and extremely short-lived. So I think the prediction is they're about 1,000 times the size of a proton. So capturing these, the fact that we haven't had the technology to observe these yet and to capture them and to harness them and to make something of them, wow, that's eons away, I think. Eons away. Exciting to think about, but yeah.
So Kirali, if you can sort that out by next Wednesday, it'll be fine. That'll be cool. So no thank you very much indeed. And thank you for exciting us about what magnetism can do and what the awesome work that you do with structures, with neutrons, is doing for us as a society as well. Our second speaker tonight is Michelle Simmons. Professor Simmons is the director of the Center of Excellence for Quantum Computation and Communication Technology. She has also founded the Silicon Quantum Computing Company, Australia's first quantum company. She is well known internationally and internationally renowned for her work in the field of atomic electronics. And she is in the race to build the world's first quantum computer using silicon. And I think it's a great choice. We know a lot about silicon, but making silicon work in the quantum world is just such a smart choice because it'll make it much easier to build those computers. And if we can do that from Australia, that will change the game. In 2018, she was admitted as a fellow to the Royal Society of London. and was named Australian of the Year. That's a double whammy that few people will achieve. This year she received, last year she received the Officer of the Order of Australia and was mentioned in the Queen's birthday honours in this regard. She is a pretty awesome person. She is a wonderful science communicator, and also she's an inspiration to all of us who are trying to not just understand the world, but to change the world. And so I'm going to welcome you now, Michelle, to speak to us about what you're doing.
Thanks, Andy. Thanks very much. So I'm now going to try and attempt to share my screen. We did this earlier. Let me just go back to that again. Share screen. Okay. So hopefully that's up now. Thumbs up, that's great. So I'm going to really talk to you, I'm going to take a little change in gear and talk about computing and really go back to, you know, the basis of where we've got to in the last 70 years or so. For me, this is fascinating. It's a story that I think most of us are aware of. You know, we started a long time ago, back in the 1940s with vacuum tubes. One of the first computers actually is here in Australia, but this is the ENIAC version of it, where basically they have a lot of vacuum radio valves that are using to turn switches between ones and zeros. And it really wasn't until 1947, and 80s kind of hinted this, where we started to look at semiconductor materials. And in this particular case, it was germanium, but the first transistor was made back in 1947. And what we realized was, rather than having these big bulky tubes where you've got, you know, literally thousands of them to operate a computer that you had to undo every time one of them failed, if you could actually make all the transistors on one chip, in this case it was germanium, but it's since become silicon, you could actually integrate them all onto a chip to form an integrated circuit. And if you could then basically build lots of different components on a chip, so put lots and lots of transistors on there, eventually build up larger and larger until you get a computer. Now that's something that we all now take for granted, but it is a fascinating industry to watch. It's obviously started before my lifetime, but it's something that I've been part of. Until now, you know, you can get 14 billion transistors on a silicon chip, roughly about 2 inches square. We have these server farms that are, you know, putting lots and lots of computers together in these racks, generating lots of heat, moving them out to the Arctic Circle to cool them down, until eventually, if you start to look at what it requires to make those devices now, you start to see, this is a plant in South Korea where basically they have lots and lots of equipment they use to design devices at smaller and smaller length scales. And literally this facility in South Korea costs about $14 billion to build. And so humans have engineered the ability to make devices in silicon down to the nanoscale, so literally nanoscale dimensions, where they can make billions of them on a transistor chip about 2 inches square. And the yield is phenomenal. So it's greater than a 3 nines yield to get those transistors working. And that allows us to communicate as we are now. It allows us to communicate across the globe with each other and to, you know, use computers to do all kinds of calculations to understand the world better. Now we take that for granted, but underneath all that is Moore's law, which basically shows that the number of components on a silicon chip double every 18 months to 2 years. And for that to happen, it basically means that the smallest feature size shown on the bottom there has to decrease at the same rate. And the exciting thing about that for us in particular, I guess a decision we made in Australia back in 2000 was we looked at that transition or that behavior over the last 30 to 40 years. And in 2000, we made a couple of bets in Australia. The first one was we said, okay, we're going to assume that the number of transistors on a chip is going to keep increasing at the same rate, which means the smallest feature size will keep decreasing. And we're going to just extrapolate that out. And if we can go all the way out to the top right-hand side there, you see the smallest feature size there is now towards the level of a single atom. And that was predicted back in 2020, 2000 to be 2020, which obviously is now. So that was the first bet. The first bet was we imagined that Moore's law would continue. So Gordon Moore is the co-founder of Intel, sitting on the right-hand side there. The second bet was that if that was going to be true, then why would we, rather than just continue to make devices smaller and smaller iteratively along that line, why would we not just jump to the technology that existed to actually manipulate and image atoms and actually adapt that to build devices out of atoms? And that technology is something called a scanning tunneling microscope, and I'll show you a picture of that in a few slides from now. But that basically allowed us to manipulate atoms to the point where, IBM made the world's smallest logo out of the letters of metal atoms sitting on a metal surface to form I, B, and M. So if you look on the bottom left-hand side of that screen, you see a cross-section of what we call a 22 nanometer node Tri-Gate FinFET transistor. And literally for me, one of the key things about that is that it's known that every atom in that transistor counts. So if you literally move atoms around, particularly if you take the dopant atoms, which have extra electrons, and move them 1 or 2 lattice spacings inside that transistor, it changes the switch on voltage at which that transistor operates. And so it was known, 20 years ago that every atom counts. And so the view is, if you could somehow manipulate the world at the level of atoms, could you create a transistor where you literally put the atoms in place and you build the whole transistor structure atom by atom? And there were a lot of challenges to that originally. In silicon, there's the material we wanted to use because that's what the industry's been using for the last, 5 decades or so. But to move atoms in a silicon crystal is very, very hard. You can't pick them up and move them around with these microscope tips. So we had to come up with a whole new way of building electronic devices in silicon, kind of mimicking what they do in the semiconductor industry by using a process called lithography. And this picture on the bottom right is a picture of a silicon surface that's been hydrogen terminated. So the dangling bonds on the surface have been saturated with hydrogen. We come along with a very fine metal tip of our scanning tunneling microscope, and we can literally knock off individual hydrogen atoms, exposing, in this case, what are dangling bonds out of the surface. So that basically showed that we could create an atomic scale mask on the surface, and now using those dangling bonds, bring down a different chemical species, in this case, phosphorus rust, which would bring in our quantum bits or our qubits towards building a large-scale quantum computer. And by putting a phosphorus atom in silicon, we've got 1 extra electron, and we want to encode the information on that extra electron that exists on that phosphorus atom. So that was our goal back in 2000, was to try and see if we could actually adapt the technology that was used to image atoms to actually manipulate and fabricate atoms. Now, why would we go to all that pain? And this is something that even now I still get asked this question. So to build a whole device out of atoms is something that's never been done before. If you can do it, then you can start to harness the power of quantum physics. If you can control the world at that level so that you can both create superposition and entanglement, you can actually start to perform calculations in a much more efficient way than classical computers. And so, to build that technology that doesn't exist, there's a lot of time and effort, a lot of technological challenges to do it. So the applications have to be really worthwhile. And so some of the applications, certainly when we started, there were really 2 quantum algorithms, a very fast database search, Grover's algorithms, and Shor's factorization algorithm. And they were in themselves powerful enough to kick off the field. But since that time, there are now these kind of 4 different areas in the quantum computing space where we've got basically optimization problems, machine learning problems, quantum simulation, prime number factorization. And there are now over 60 different quantum algorithms that are actually registered on a US government website. And the key thing for me that's exciting about this field is if you look at some of the pictures around there, it will give you a sense of the companies that are investing in this. So you've got companies like UPS, the United Parcel Service in the US, is looking at the fact that, every day its drivers travel all over the world, or travel all over, in particular in the US. And they found that they could just shorten the distance that those people travel every day by just 1 mile. They would save their company $50 million a year. So those is what we call optimization problems that are out there. And UPS is one of the companies that's interested in the quantum regime. You've got machine learning on big data. You've got things like artificial intelligence. You've got machines that are looking around, trying to figure out self-driving cars, looking at lots of amount of information that's coming in and trying to sort that data out. And so a lot of the companies like Google are investing in this to look at the huge amounts of data they've got to sort through. You've got quantum simulation. So one of the key applications that people have identified as probably one of the first applications is looking at quantum simulation, to try and simulate chemical reactions or catalysis reactions, which are very difficult using classical computers. So typically once you get past around about 20 atoms, it becomes very hard for a classical computer to start to work out all the different chemical reactions that occur, all the bond breaking and forming that happens, to try and work out what the ground state of those molecules are or how the chemical reactions occur. And so one of the processes that people have identified is something called the Haber-Bosch process, which is breaking a nitrogen triple bond to create fertilizer, to release nitrogen into the soil. That's a process that's very high pressure, high temperature, takes a lot of the world's energy to actually create that nitrogen atom for fertilizer. And yet it's something that is well known to be a limiting factor for creating fertilizers that feeds the world. So finding a catalyst that can actually break that triple nitrogen bond is something that quantum computers are looking at as one of the first kind of applications. And then that extends way beyond that in the long term, obviously, to the hope that we'll start to look at drug design and how different drugs interact with the human body. And that's something that's very exciting, and I imagine will keep growing in the next couple of decades. And then the long-term goal You know, if you could build a very large scale quantum computers, you could start to do things like prime number factorization. So this is basically working out what the prime factors are of large numbers and using those to basically decrypt codes. There are lots of industries now. I think it's a very exciting time that are investing in this, looking at it. So whether it's car industries, big defense industries, finance industry, it pretty much hits every sector that has lots of data or has lots of complex calculations that take just too long to do on a classical computer. So, you know, it's as of today, there are computers out there that are starting to show that there is an advantage to using quantum states over classical states. We're really at the very early stages of that, but there's a lot of promise in being able to build larger and larger scale quantum computers. Well, so one of the other things is there are lots of different ways that you can build quantum computers. So unlike the classical silicon industry, really for a long time, all the classical computers have been built mainly in the semiconductor materials. But in the quantum world, there are now multiple platforms that people are investigating across the world. And I put some of these up here just to give you a sense of the excitement of the field. There are lots. So we've got silicon spin qubits on the left. We've got superconducting loops. So Google and IBM are some of the leaders in that space, along with Rigetti and Quantum Circuits in the US. And they're looking at using literally superconducting materials to create these magnetic loops, which they can create quantum states in. Some of the first people out of the traps, no pun intended, were ion trap quantum computers. These are using ions inside a vacuum system that are controlled by lasers. You can use vacancies in diamond material, topological qubits. There's companies like Microsoft are looking at this for error protection for their qubits. There are some exciting results coming out in optical qubits, and Australia has great expertise in optical qubits as well. And then neutral atom qubits. So these are all different, literally physical systems in which you can encode quantum information. And the exciting thing about it, you can see, is there are companies coming out in all this. So there is, as of today, no real working quantum computer that can do a commercially relevant calculation. Yet there are all these startup companies, both enormous companies, government labs, small companies, all across the space, from the hardware development through the software and all the way up. So I've just focused here on the hardware platforms. So that's the excitement behind the film. But ultimately, you've got to choose. Any kind of scientist in their life has to choose something that they're going to commit their life to. And so we really chose silicon. So at that time, when quantum computing was starting off, myself in particular was working in a gallium arsenide material, another semiconductor material in the UK. And I looked at, if you could build a quantum device, one of the key things is you have to build a computer. You have to be able to build the same device twice. And you've got to understand how to optimize that device and keep replicating it. So going around that cycle of building, testing, and improving every time you do it, and replicating what you can do and understanding why you can replicate, for me was at the heart of the choice that I made. And literally as a big Australian team looking at silicon. So we decided to choose silicon, and I'll show you in a couple of slides why that is. But the key thing for us is to use silicon, we want to literally put single atoms of phosphorus into silicon and encode the information on the extra electron spin and nuclear spin of those phosphorus atoms. And the technology that we use to do this is something called a scanning tunneling microscope. It's just a schematic of it here on the left, a very fine metal tip. We bring down to the surface of our material. It's under vacuum control, so you can see on the top right-hand side, it's an ultra-high vacuum system. Once we get it very close to the surface, we can apply voltage to that and measure the current that transmits between the edge of the tip and the semiconductor surface. And in such a way, by controlling that current and keeping it constant, we can scan the tip using piezoelectric control across the surface until it deflects over each of the atoms on the surface. So that's how you can actually image the surface, but you can also apply voltages to that tip, and it kind of electrostatically acts as a way of connecting atoms on the surface, pulling them up to the tip and breaking the bonds from the atoms in the actual crystal structure beneath. And in some ways, IBM were able to do this by putting metal atoms on a metal surface. But as I indicated at the beginning, doing it in silicon is a little bit more challenging because all the bonds are strongly formed. So we had to do this using a process of putting down a hydrogen resist, opening up holes in the hydrogen, and then bringing phosphine in to bring our phosphorus atoms in. So that's the technology that really, and I guess one of the things I love about Australia is the ability to adapt different technologies to do different things. We took a microscope that was an imaging tool. We've adapted it to a lithographic tool that actually creates atomic scale masks. And since that time, we've been able to demonstrate that we can actually build complete devices by putting atoms into silicon and encapsulating them with silicon to build these quantum bits or qubits. So the kind of schematic of what we're trying to build at the end of the day, it's a very simple schematic. It looks so easy on the page, so on the screen to see this. Individual phosphorus atoms with electrodes above them. We're putting voltages on those electrons, putting the whole thing at very low temperatures. so in cryogenic liquids down to millikelvin temperatures in a magnetic field. And we're using the spin of the electrons on the phosphorus atoms as our quantum bits or qubits. So they either align with the field, gives us one energy state, or against the field that gives us another energy state. And by controlling the voltages on the electrodes in the magnetic field, we can actually spin the electron spins all the way around what we call a Bloch sphere. So we can get it pointing at the North Pole or the South Pole, or we can create entanglement between those electrons on the different phosphorus atoms. And so the advantage of why we would choose silicon, ironically for me, is that it's what we kind of call the equivalent of an ion trap system. So we're putting atoms into a silicon crystal. The crystal itself is completely neutered. So there's nothing in there. We can get rid of all the nuclear spins and it acts like it's a vacuum. And so we can put atoms as close as we want with this technique of lithography, and we can get these what we call very long coherence time. How long can we hold the quantum state for? And how well can we accurately control the spin of the electron on that state? So silicon atoms in the solid state, they've demonstrated the longest coherence times with highest accuracy. That basically means you can do lots of calculations on the quantum bits before they lose their quantum states. By putting it inside silicon, we're actually creating a very low noise environment. We're using material that's been studied for 50 to 60 years. We can engineer every aspect of the device so that we can replicate the device. And over the last two decades, we've actually demonstrated multiple architectures and patented along the way to build a whole-scale quantum computer. So that's where we're heading. We've got patented architectures, technology to build it, and we're now in a race to get there as fast as we possibly can. And to do that, we've now created a company which is aligned to our Center of Excellence to actually build the hardware here in Australia. And so just to understand how long will that take, because it is a race and it's very exciting to be part of that race, but in a way we have to map out our roadmap. And the way we've actually done this is to look at the original silicon industry, look at the development of the first transistor in 1947, and recognize that it took roughly about a decade before they built an integrated circuit. So there were 8 different components they put onto one monolithic chip of semiconductor at that time. And then using that same technology, they started to get their first kind of commercial devices about 10 to 15 years later. The MOS transistor, which is the metal oxide semiconductor transistor that's used now inside silicon transistors, the first development of that was 1960, again about a decade before they got lots of microprocessors on chip, and then again another about 10 to 15 years after that before they started to get commercial devices. So that's really kind of the process that we're looking at now. We've demonstrated back in 2012 our first kind of single atom transistor, and what we're doing now is heading to what we call the 10 qubit quantum integrated circuit. So there's our 10 kind of phosphorus atoms schematically shown there with all our electrodes that allow us to put information in and off that. On either side, we have something called a single electron transistor. It's called an SET, and that allows us to input information and read out the information from that 10 qubit structure. So that's really what we're heading for. And as I said, over the last couple of decades, we literally are going through systematically showing how we can put information to an individual atom, how we can create entanglement between the atoms and control those, how we can get single qubit gates and 2 qubit gates, and ultimately build a 3-dimensional error-corrected architecture. That's where we want to head in the long term, and that's kind of shown on the bottom right-hand side there. It's a very exciting field to be in. One of the realities of being in the quantum field is that you need a lot of infrastructure. And so being at the University of New South Wales has been fantastic. Being part of a Centre of Excellence has been fantastic. But over the last few years, we've actually now established this company that's working towards building that 10 qubit quantum integrated circuit. It's heavily funded by industry, university and government working together, which I think is quite critical for Australia's future. And as I said, our long-term goal is actually to build the quantum computer chip here in Australia. Well, there's an indication of the race, the companies that are coming into this. This is just a snapshot. I've already given you a sense of that, but also the amount of funding that's going internationally to big coordinated centres. Australia was the first centre to have a first country actually to have a quantum computing centre back in 2000. Obviously, we've been going now for 2 decades, but you can see there's lots of countries in the world coming into this space and lots of companies. And you can see down at the bottom there, lots of government labs are coming into silicon. So the race is definitely on. It's very exciting. But with that last thing, what I'll leave you is, one of the things that's exciting for us is all the different infrastructure we have here in Australia. We are leading the world in this space. We can design, build and test our devices. We can do that within 1 week with a new generation of devices. And we actually build the quantum chips here. One of the greatest things I remember being in this building was very recently a young boy about 12 years old was walking through with his mother, and he was looking through the window. And I heard him say to his mum, "Mum, is that the quantum computer?" And that was very exciting. So it's definitely inspiring the younger generation, and it's great to be able to share that with them. So thank you.
Great. Thank you so much, Michelle. I think that is such an interesting journey, because it's a journey that started with a dream and now has a plan. And then the next thing is for the plan to work. And it's awesome to have you explaining how that vision really started in a very practical way, but you've got to do all the work to make it happen.
You sure do.
If you were to look at the kind of the opposition that's out there, what do you think the edge is for us at the moment? Is it that we chose silicon? Because I still think that's awesome. I was involved years ago in optical devices and silicon, and
Yep.
It's a material we know about. But do we also have an edge because we're far away from people, and in a way we think a little bit differently? What's your sense of what we do?
I do think that. I think it's because we chose silicon fundamentally, and it was I think that the decision at the time was really based on what's the best way to make it. And so we were not, the people that kind of came together right at the beginning were not experts in silicon. And, and when we came into it, I guess a lot of the experts in silicon, particularly from Silicon Valley, would look at it and say, there's, 1,000 technical reasons why this is not going to work. And I think, part of the reality is that if you have new fields, particularly if you're working in a university environment, you're seeing things that are, really honestly haven't been developed or seen before. So you're really pushing the boundaries of what human knowledge is. And so you see the world in a slightly different way. And if you're, I think one of the things that's been amazing for me is the silicon industry is an amazing industry. The engineers in that industry are phenomenal. And so they've literally replicated devices that nobody would have imagined when they were young. And I think for me now with the quantum world, it's a whole new generation of devices and a different way of thinking. And so I think, being in a university environment and seeing that kind of cutting edge stuff, but then, actually being in Australia, like you're saying, be remote from the rest of the world. So not tainted with all the negative reasons why things are not going to work, but with the, with the practical, the practical sense that Australians have of let's give it a go and see if it can work. Write everything down that could possibly go wrong and just one by one systematically go through and work them out. And that's, that has been terrific. And I've loved being here with that Australian spirit. And I think now, industry is now starting to get to the point where they can see a lot of the stuff that we're learning is relevant for them, for their classical industry, but they can also start to see actually that we do have the control to put atoms there and build devices at that length scale, which I think, 20 years ago, they were really very doubtful of.
Yeah. Last question. If you're a young person like I was at about the age of 17, deciding between writing poetry or doing physics, what's the answer?
Oh, that's tough. Both. Here you go. So I love painting and I still manage to paint in my spare time, what little I have. Yeah. But I think honestly, the answer is to do whatever every day makes you want to get out of bed and get to work. Whatever that is. And if you can do both, then even better.
Yeah, and science is pretty cool, isn't it?
It really is. It really is. I can't wait to get to work.
Excellent. Well, thank you so much for that. You've certainly given us something to think about. And somebody who understands the history of silicon in Australia in a very profound way, and who is also the chief scientist at CSIRO is Dr. Kathy Foley. A truly remarkable person. She's worked on superconductors, looked at actually magnetic materials, which we've already talked about tonight, and using those to really develop entirely new devices. So Kathy in her working life has developed entirely new systems based on using very, very clever materials. She has great leadership in so many different domains. One of them is the very practical, the big sort of practical award that is given every year to engineers and scientists who make a distinctive contribution, the Clunies Ross Medal of the Australian Academy of Technological Science and Engineering in 2015. And as I indicated right at the beginning, she has also this year become a member of the Academy of Science, an honorary fellow of the Australian Institute of Physics, and also an officer of the Order of Australia. I don't know whether anybody else will do that in the next generation. It's a remarkable achievement. You are a remarkable person, Kathy, and I'd like you to tell us about how we're going to create a quantum industry in Australia.
Well, thanks, Addy, and it's really lovely to be here. I'm just going to share my screen and hopefully it's going to all work. So here we go. So I'm going to be changing gears a little bit to try and see if this is one where I'm hoping that this is the presented, that you're seeing the right sort of thing. Can you thumbs up? Great. So I'm changing gears, as I said, to look at how do we turn all this great science into something that also not only is brilliant, exciting, creating new opportunities, but is something that's going to help Australia be healthy, wealthy, wise, and be the nation we want it to be. And coming from CSIRO, I guess this is something which has been part of our way of looking at the great research we do in Australia and how we can turn it into something special. But the thing that's really interesting is, so far you hear this and you think, wow, is this really hard? Is this something which has nothing to do with me? Well, I just want to remind you that it can't be too hard, because you can go to any shop and any bookshop and you'll find a whole series of quantum physics, quantum teleportation, a whole range of things for babies. So good starting point. But I want to go back to how come I got involved with looking at, can you make a quantum industry in Australia? And this started in the Australian Institute of Physics Congress 2 years ago in December 2018. And some of the people who work in quantum research across Australia came to me and actually lured me to a breakfast and said, what can we do in order to create something that makes this research we're doing into a possible industry in Australia? How can we see this turn into economic value for the investment that's been made? And so I went back to work and asked my boss, can I have some money and work with our CSIRO Futures team? Because one of the things we have to remember, when we're going to make something commercial and take it from the laboratory, it's not just the science, but it's a whole lot of other things that go around it. There's the economics, there's the collaborations, there's the need to understand the customer. We need to be able to think about how we can deliver something. And so we actually have a team of people who've gone about doing this, and they know how to take science and turn it into something which is a roadmap of what is needed to make something into an industry for Australia. And so they've done this in a number of areas, such as space, cyber, hydrogen, which you've probably heard about, and they turned their hand to looking at our quantum work. So when you're going to sell something, the first thing you have to think about is, what have you got to sell? And we've got a lot to sell in Australia. You can see here that around the country, we have a huge number of researchers working in this field, and that we've had over the time extraordinary amount of investment, as you saw from Michelle's talk, over, since 2000, but actually before that, because my own research was in superconducting electronics, which is also quantum materials and quantum devices. We've been doing some great work for a long time, and it's something which has been sustained. And we're getting to a point now where we've got a whole lot of products and possibilities that can be realised. And then we need to have someone who wants to buy these things. And so you heard from Michelle about the quantum computers and where they could be used. But there's also other quantum technologies as well, such as sensors and devices and things like that. And they can be used for health in order to accelerate drug development, and also even for being able to detect things and be able to look at imaging our bodies. We're also able to use them for defense and security, such as what would happen if we're in a situation where our GPS was denied, so that we'd know where we are. We use them for mining, to be able to look for our natural resources, not just mining, but also water resources. And more recently, looking at how we can improve our communications, making them more secure, but also able to have the broader bandwidths that we want, and communications that are able to be at the cutting edge, which we know in this COVID world has been absolutely critical for us to be able to cope with that. So when we look at Australia, we already have a fledgling industry, which is so exciting to see. We've got 14 quantum-related private organisations around Australia. We've already got over $125 million investment over just that 2-year period. And you can see here a list of different companies that we've had coming and set up where we're seeing research translated from our laboratories, just like Michelle has done with the silicon quantum computer, and as well as other companies such as quantum enhanced cybersecurity solutions with Quintessence, which is the oldest quantum company in Australia. We've also got quantum medical imaging with LuciGem as an example, and precision timing devices for diverse applications such as CryoClock. And in fact, we have with Q-Control, one of our companies which has been growing internationally at such a rate that last year it was identified as one of the top 10 global startups. So we're on a really good starting point. However, as Michelle mentioned, this is really competitive. And as every country that is interested in having technologies that really are breakthrough, and you can see the flags here for many of the different countries, are absolutely investing big time. And you can see here that China, for example, has reported to be committing of the order of $10 billion towards quantum R&D because they see this as being so important. But one of the things which we need to do when we're competing in a world climate like this, where there's lots of money being flown around, is that we have to be smarter and be able to make sure that we can turn what we have here into something that will create an industry. And one of our challenges is to see, as a science sector in Australia, can we be smarter by having this ecosystem approach to commercialisation? And this is something here which is sort of trying to show how we're trying to get the Australian science sector to be seen differently so that we have different parts playing different roles, such as universities, looking at taking things from basic through to commercialisation. Organisations such as ANSTO and CSIRO, I've just used ANSTO there as an example, are publicly funded research agencies who are really good at doing things like this, where we're creating a roadmap to be able to bring the community together. And then at the other end with production, where it's the industries itself, which are some of the things started up already. We're seeing multinationals such as Microsoft coming into Australia to be able to set up shop because they can see the importance of this. And also governments such as state and federal who are actually part of the organisations that actually are going to buy some of these quantum systems in order for them to be able to do their business properly. So when we did the roadmap, we went through and consulted very broadly. We talked to 100 stakeholders across Australia, both government, industry and researchers. And we went through and identified a vision, value and some action. So the vision was that we had consensus that we think we can have an Australian quantum technology industry. We started off having one of the first two computers in the world you saw a picture which Michelle showed at the beginning of her talk with one of those first basic computers. We actually had the second computer in the world in Australia, but we didn't see it turn into creating an electronics industry for Australia. This is our chance to turn around and do it right this time. We've also undertaken an economic analysis and shown that there is the potential to scale this opportunity and be able to see some return on the investment of our research so that we can reinvest it into new and future things. And then what we did was create an action plan that's going to enable us to turn this all into something which can capture that value. So our vision is that by 2040, so it's 20 years away, that we're going to maintain our competitive strength in quantum technologies, which means we have to keep investing in the research. But we're also going to make sure that we are creating the opportunity to generate IP, that we're able to commercialise these applications and set up the structures around us in Australia so that we can have that industry. So there's lots of value to be taken. Addie mentioned it's over $80 billion industry forecast by 2040. And we think by our economists going through that we can hive off some of that so that we can create a $4 billion revenue by 2040 with creating about 16,000 new jobs. And for those of you who are at school, these are the sorts of jobs that you will be working in. And they could be not only just in computing with quantum computers, working with Michelle and her business, where there's going to be 10,000 jobs and creating $2.5 billion a year in revenue. There's also more near-term sensing and measurement, where we're able to look at about $1 billion there per year coming in, with creating about 3,000 jobs. And then in communications, about $800 million a year with about 3,000 jobs as well. These are all things which we know, and this is a conservative approach in the way we did our economics. These are things which we can do now, or be prepared for now, so that in the future we've got great opportunity. But to do that, we have to have some actions. So the first one is, as a country, we need to focus and coordinate our quantum industry development efforts. And this is what we're seeing. It's been absolutely fantastic to see, even though Michelle said there's a lot of competition here and there's a lot of people working to try and break through some of these difficult things, making probably the most complex machine that will ever have been created by the time it's succeeded. What we're seeing is extraordinary interactions, collaboration and partnerships. We also need to make sure that we're building up this workforce for the future, because you don't actually find too many quantum engineers around being able to be employed. So those of you at school now need to think about taking the sorts of courses and doing the preparation, because by the time you've finished your training, there will be a whole new industry there looking for you to be part of that workforce. You also need to have the infrastructure around that as well, and I'll talk a bit about that in a minute. And I mentioned before, the collaboration and partnerships are needed, because it's not just a single person or a single university or a single research team that's going to make an industry. It's actually the smorgasbord of a whole lot of different things working together, and the partnerships and being able to work together to make sure you've got all the different industry partners there working together to be able to make sure that we've got a full industry there. And then to do this, we have to have readiness. As you mentioned, we've got a lot of technologies that are very different, will have a major impact on things such as banking, with Shor's algorithm being able to unpick current ways of doing security encryption. We will need to make sure that all our different businesses, from whether it's banking, government, health, defence, that they're actually prepared in time, so that when these new technologies come, they've worked out what the risk assessments are, they know how to manage their security and embrace quantum cybersecurity, so that then they're able to embrace these and really have successful future businesses. So progress so far has been that we've gone through and got the roadmap, which you can find on our website. We've also got to a point where we've had, for example, the Pawsey Supercomputing Centre over in Perth has partnered with a new startup company coming out of ANU, Australian National University, called Quantum Brilliance, which is developing a add-on to the Pawsey quantum computer to create the first quantum supercomputing hub for innovation. We've also seen that the interest in establishing an independent peak body representing the quantum industry. So that's still in the thought stages, but that's something which we're really looking forward to seeing set up. We've seen the New South Wales government invest heavily into quantum computing, setting up the Quantum Academy, and they've looked at this roadmap and endorsed it, and they're going to be part of our delivery plan for it. We've got the Australian Defence Department just recently released its More Together strategy, and one of their star shots is looking at quantum technologies. The University of Queensland and the Australian National University and other universities have expressed a huge interest in making sure that they take some responsibility of all those actions. And there are also many other people who, from whether it's industry, international groups, and also other parts of government, both state and federal, we're seeing this roadmap as a world first and showing that we're sort of spearheading our way to make this industry really happen. Finally, one of the things we're planning to do, or in the process of doing, is setting up a sort of an informal task force. And I'll point to that in a moment. And the reason why I'm just going to quickly go through and explain just briefly what it really takes to take something from the lab. So what you're looking at there is my own research from many years ago. You can see in the 1990s and more recently. And this is something where we were taking superconducting, high temperature superconducting material and making a device that can detect very small magnetic fields. And what we were able to do is take that, make a device, take it out into the field, which is, you can see in the early 1990s, there in the middle of Australia, looking at can we find deeply buried mineral deposits. And from that, we were able to show that we could detect mineral deposits and be able to turn those detections into future mines. And this is the Cannington Silver Mine, which we did in the 1990s, identify and help delineate the ore bodies there so that BHP were able to bring that online 18 months earlier than previously thought. So that sounds fantastic, but to make something commercial takes a lot of effort and time and development. So you can sort of see in this picture here, as you go down from our early experimental method through the different steps to have different systems, because it's not just the device, but it's a whole package around it, worrying about batteries, hardware, cables, connectors, doing experiments. You can see a picture there where we went overseas and did some of our experiments. You can see in the Arctic up in Canada, and that was able to do some tests there. And our SQUID system, or our superconducting sensor, was buried in the snow. And you can see it started off as an experiment in a plastic Woolies box, getting to a point where it's fully packaged into something else, so that you've got a full system here. And there it is there with all its electronics and readouts and things like that. So this, you can see, takes a long time, and it takes a lot of effort, endurance, but it's also so rewarding. So next steps, we need to make sure that we work with business, with governments, in order to make sure that we've got a level of preparedness so that when quantum computing turns up and is going to be a disruptor, that we're ready to be able to take on board the risks and just have a smooth transfer to that. For example, social media, when it crept up on us, we probably didn't have the regulations in place. And so we've seen some of the issues relating to fake news and all the stuff that goes with social media these days. And that's something we want to avoid. So that's preparedness is going to be really critical so that we're well placed to make the most of this quantum revolution. The other thing we need to have is the translation hubs, which will allow us to have places and support so that companies can come in and scale up. We've got, for example, 2 quantum startup companies coming into a translation hub we've set up at CSIRO, which has been operating for some years now, where we've had a number of different companies come in, develop, grow, and then mature out and become quite big companies. And having that infrastructure around a startup to allow them to mature and be able to achieve that is really critical. I've mentioned already that the Pawsey Quantum Brilliance team have established a sort of a collaboration, and we're going to see more of that, where different parts of the sector coming together to support each other. And then we've also got the Australian National Fabrication Facility, which is actually looking at how it can mature to the next stage. So instead of just, as well as supporting the fundamental research that is being done to develop these devices and systems and materials, it also will look at being able to be a translation hub as well and make the most of its national footprint. And then finally, one of the things we do need is these self-forming networks. We've had that so far in order to create the roadmap, but we need to get people involved. We need to form the networks that will help us take the actions from our roadmap and make them into reality. We also need to make sure that we get the feedback of what we need to do, because things are constantly changing. And our task force, which is a self-forming network, is being launched soon. And I encourage any of you who are interested to make contact if you want to be part of that task force. And I encourage you to go onto our website and read our roadmap and see how you can contribute to becoming part of Australia's future quantum industry. So thanks very much.
Great, thank you very much, Kathy. Really appreciate that vision that you've created that takes us out into the future. And I get a sense as well that it gives a pathway for people who perhaps don't want to be quite so sciencey, but might want to be interested in business or startups or how you do the engineering perhaps and a little bit less of the science. And really want to ask you about how you made the choice to jump into science at the time you were transitioning out of the school into the world of uni. Was that a simple step, or how did it go for you?
So when I was at school, I didn't know any scientists, and I come from a family of architects and business people. And so I was seen as a black sheep, but I have always been fascinated by the world around us, and particularly solids. So when I was at Macquarie University, I had the great opportunity to start off doing science. I was going to be a science school teacher, which is a very laudable and really important career. But I have to admit, I got, I guess, taken over by the love of doing scientific research. The idea of doing something which no one has done before, creating new knowledge, thinking through how you can turn an idea into some reality. And in my case, trying to understand materials and then turning them into something that is practical, and then taking that practical thing into a system that can then be used and makes a difference to someone is so addictive. You just can't not do it. I'm lucky that after CSIRO, after working, finishing my degree at Macquarie University, I got a job at CSIRO, and 35 and a half years later, I'm still there, having done lots of different jobs along the way. And it's, I can only encourage young people listening today to say that it's a most wonderful job. It's so varied. There's so many opportunities and so many different parts of the chain as you go from the discovery through to creating something that is having impact, that there's something for everyone.
Thank you so much for that, Kathy, and thank you to all of our three speakers. What we're going to do in a few, and in fact you can start now, is those of you who are watching on YouTube and you might want to ask some questions, what you need to do in order to answer those questions is to just refresh your YouTube screen, and that will allow you to give us your questions. So some of you have submitted questions already, but you may also want to just refresh your YouTube screen at the moment. That'll allow you to ask some questions. That takes about 10 seconds, so we're going to take a 10-second break, and if you can blink at each other and get ready for in about 10 seconds time, we'll be ready. So this is a question to all three of our panelists tonight. I came out of a family where my mum was a psychiatrist. She worked right through the time that I was at school and so on, and I found that fascinating. By the time that I could start to read, she was putting science books in my hands, and I found that remarkable. I know that each of you are parents as well. How cool is it to be a parent and to be a mum and to live in this world of science? What would you tell somebody who's a bit worried that that's all too complicated? I don't think it is, because I've lived that life, but perhaps you've got some ideas.
Well, I've got a blended family of 6 kids, 3 of my own and 3 stepchildren. We've been together through 6 HSCs, lots of heartbreaks and lots of joys, but it's the most wonderful thing. So, and in many ways, research is very flexible, and you can actually work around the different needs of your family. I know when my kids were smaller, I probably had that plateau period where I focused on raising my family, but then they got older and more independent, and then I was able to see my career fly after that. Be interested to hear from Michelle and Kirralie.
Kirralie, any thoughts on that?
Yeah, so it's interesting actually. I guess that Michelle, Kathy and I are sort of at slightly different phases of our career and of our families. Certainly throughout my career, I've noticed that support for women in STEM has been increasing and improving just exponentially. Companies are now really supporting women and families in general for being able to continue to do what they're passionate about, what they love, which is their science, their work, and yet still raise a family at the same time. I mean, just for instance, you know, at ANSTO, as I had a preschooler, they opened a preschool or a daycare center on site, and that was it meant the world that I could then drop my child at work at the daycare center and then come into work. So that sort of support was wonderful, and even things like the AIP. You know, if I wanted to go to their Congress, a couple of times I was able to receive the generous benefit of a childcare bursary, which meant that I could bring my husband and my son to the Congress with me. So it meant I could still focus during the day and keep engaged with the science at this Congress, and yet still have my family with me and have sort of family time in the evening. And that was totally invaluable. It was a perfect opportunity. And I think that support networks are, you know, improving even as we go forward from now.
Fantastic. Michelle.
Yeah, look, I think it's funny. I know there's a lot of discussion now about work-life balance, and you know, everyone frets about whether they get it right or not. And I think the reality is that, you know, there's no such thing. There's no such thing. I think everyone has a different set of circumstances, a different, you know, environment that they're in, and so it really is. It comes down to what you want from life and what you're prepared to put in. And so for me, I think one of the things I've certainly encouraged a lot of females from is not to shy away from doing hard things because you think you want to have a family, you can't do both. I think you can do it all, and it just depends on where you put your time. So as long as, I mean, I have to say the one thing that I've learned is you got to choose the right partner, because if you've got the right partner who understands what you're doing and can share it with you, then, you know, you can do whatever you want. You can achieve anything. So choosing the right partner is quite critical, as well as, yeah, choosing the career you love.
Yeah.
And can I just add, I guess my kids are grown up now, and they started long daycare when they were 11 weeks old. And so I've done the experiment, and they've grown up to be wonderful, loving people, even though I work. So it does work, and you can have a wonderful career in science, and children that grow up and think their mum is still okay and love her dearly.
I think that's true. I'd second that. I think you can, and having children is fantastic. So you should always make sure if you want to have them, you have them, because they're terrific.
Yeah, it's amazing. I had this awesome mother who would have been 103 this year, and she taught me so much about life, and I'm still growing up in a way, and pretty soon I'll be able to do the awesome stuff that she did, and so that's an encouragement to me. So thank you for those wonderful answers to what I think is quite a significant question. But I think we are in a changing world, and to do what you love and to be able to really hold it all together is actually how we want to create the world for the future. So that's part of the journey of the quantum computer, is the awesomeness of women leading in science and taking us into the future, which has been what tonight's all about. But I'm going to go to other people's questions now. And I'm going to start off with a question from Michelle Ben from Tallawong State High in Queensland. How cold does a quantum computer need to be? And I think the really interesting part of the question is, can we get a room temperature one sometime?
Yeah, look, there's a lot of people would love to have quantum states that behave well at room temperature. And there certainly are systems, obviously optical systems work at room temperature, and NV Diamond do work at room temperature. But I think at the moment, I think the reality is you can't have everything. And a lot of people want to have large scale systems that are very coherent, where you can actually manipulate lots of quantum states. And my instinct is you're going to still need very low temperatures. There's been some exciting results recently about trying to get semiconductor systems working at high temperatures, and that's still, cryogenic liquid temperatures. But the reality is you've got these fragile quantum states, you want to control them. So you need a controlled environment, the lowest temperatures, relatively high magnetic fields, and controlled environments. I think you're going to need them for quite a while. So we really envisage the first quantum computers will be server systems that you access online over the web, and they're in a nice controlled environment with the best operating conditions for the qubits.
Yeah, thank you for that. I'm going to go to Kathy now, and there's an interesting concept which I'm not very familiar with, but you may be. Quantum cobots or quantum robots. Are they just a dream at the moment, part of science fiction, or is there an opportunity to do cobots?
I imagine they are science fiction, but the thing is, most of our good ideas come from science fiction and then become a reality. I mean, those of us remember Dick Tracy watches or something, which were thought of as never going to happen, and now they're just something which people wear all the time. So I think it's a concept of being able to have, I guess, the idea of quantum, not just classical science, classical physics running something, but the idea of the extra information and extra science that goes into being able to manipulate things, or being able to have something that's thinking, such as getting to a point where we understand cognition, so that's probably got a quantum aspect to it. That is something which I think is down the way a bit, and we still haven't quite come to terms with. But it's, I'm afraid, still a science fiction, but something which will inspire us.
Fantastic. Thank you very much. Kirli, Rod from Como asked this question. With your ability to use neutrons, how can we use them to do a better job of understanding quantum technology?
Yeah, absolutely. I certainly think that neutrons can play a vital role here. And a lot of this comes down to the material research, learning and understanding a lot about materials. Now, I think both yourself, Adi, and Michelle have mentioned that silicon is a really important material because we know so much about them, about silicon. So, but certainly other materials are absolutely sort of worth investigating in terms of what their properties are, how we can manipulate them, how we can change their properties, and therefore how we can then implement them into technologies of the future. So yeah, absolutely. I think we should be on board, and it's an exciting time with this quantum roadmap just released, and I think that ANSTO can play a significant role in the research there. Absolutely.
Great. Thank you for that. We're going to drift a little bit into biology now, and I wanted to just ask this perhaps of Kathy, and I'm going to come to Michelle after that. Antiviral drugs, and we're living with COVID at the moment. Is there any intersection between dealing with the viral problem that we've got with COVID and the quantum phenomena that we are looking at? Is this quantum world able to help us solve the COVID crisis?
So I'm not sure we're there yet. There's two ways to think about it. The first is, can we actually understand how biological systems work? And there's a whole emerging field called quantum biology, which is looking at, can we understand cognition? Can we understand photosynthesis properly? Can we actually design or understand how things like viruses such as COVID, can we actually understand how they operate so that we can then get in there and have a design a drug that really gets into the core of their critical bit that causes illness. They've sort of mastered that to some extent with flu, but it takes a long time. And there's the idea that if you could understand the quantum biology of living things, that we would actually be able to get to those solutions faster. That's one aspect. The other, though, is can we use quantum computers when we've got them to actually design drugs faster and be able to fully understand simulations so that we can get in there and do, it's almost like real chemistry, quantum chemistry, in silico using Michelle's quantum computer when it's complete. And that's going to allow us to fast track the development of drugs for purposes that are of the nature of a pandemic. Now, as we get a bigger population, the number of pandemics are probably going to increase in frequency because of the potential of humans and animals living closer together. Zoonotic type virus transmitting from animals to humans is going to start happening probably more frequently. And so we really need that. And that's one of the possibilities of a great outcome from having a quantum computer.
Thank you so much. That's a really helpful answer. Michelle, I'm going to follow on with that from what Kathy has been saying. What are some of the other sort of top applications of quantum computers that'll be game changers and really make us think that the current computers are kind of average?
Yeah, look, I think I tried in my presentation to highlight the ones that I'm particularly keen on. So I think quantum simulation, so new materials and drug design, catalysis are critical areas that are closer to hand. But the reality is you need a large-scale quantum computer that's error-corrected in order to be able to do that. So quantum simulations at the beginning, there's going to be a period of time where you might be able to get away with that error correction, but in the long term, any kind of really powerful computer is going to need that. So we're on a long journey, and I guess part of the challenge is to find the commercial applications that are nearest to hand, and certainly simulations, catalysis, drug design is probably still a little bit further away from that, of the areas that people are looking at. As well as looking at large databases and optimization problems. So a lot of the finance industry's identified areas where they can see quantum algorithms coming in, but they're highly mathematical. So it's too early, I think, to say where it's going to come. But I think if everyone had to bet, they'd say chemistry, simulation, materials would be the areas that you'll see it come in first.
Thank you. That's really helpful. Kirili, question for you, a little bit technical, but something I worry about. Quantum entanglement. What is quantum entanglement and how does it work?
Yeah, okay, quantum entanglement. So this is something that I think Einstein related to by saying it was spooky action at a distance. And it's sort of the basis for something, quantum teleportation. I guess everybody's seen Star Trek, and you know that quantum teleportation involves beaming up somebody from a planet to a spaceship. And so this is involving the quantum concept of entanglement. So before I talk about entanglement, I just want to say one thing. The way that it works at the moment is that we're transmitting, for quantum entanglement and quantum teleportation, we don't transport matter from one place to another. We transport information. And so this information is tied up in an entangled pair of particles or photons, for instance. So just say we have a pair of electrons, a spin up and a spin down. We know that they're always going to be opposite each other, but they're entangled. We don't know which direction they're facing, but we do know that they're going to be opposite each other. So the idea is if we can separate these two entangled pairs of particles, of electrons, say, without measuring them, we just put them in two places, location A and location B. And then say we have another atom or ion or photon even at location A that we want to transport to location B, then we can now compare the state or the wave function of that new particle that we want to transmit, and we can compare it with our first entangled partner. So then we tell part B what the relationship was, and we can reproduce the same wave function at location B. So we're not transmitting particles or mass across vast distances, we're transmitting information. And so this is via this quantum entanglement. And one of the neat things I think about this quantum entanglement is that it's almost like a lock and a key. So we know that part A and part B are going to always be opposite each other in this entangled pair, but we have no idea exactly which state they're going to be in until we measure them. And so therefore we can't decrypt the message as it goes from one to the other. It's a really secure way of transmitting information. So you can imagine the possibilities there.
Absolutely. Now, part of what you've decrypted for us is we've come to the point where we have to wrap this up. What an awesome panel. What an incredible group of people to have this discussion. And to bring it all together tonight, I want to say that I think it's been awesome to have you here, but people have made it possible. And it's been made possible by ANSTO, the Australian Institute of Physics, the Royal Australian Chemical Institute, the Royal Society of New South Wales, CSIRO, and the University of New South Wales. I think it's been really, really awesome to have these institutions joining together in a kind of entangled way in order to tell us about the quantum. And I'd like to now introduce Dr. Scott Martin, who's the chair of the Australian Institute of Physics in New South Wales. and ask him to bring it to a close tonight with a vote of thanks.
Thank you very much, Adi, and thank you for this opportunity to say a few thank yous here tonight. In this quest for quantum, despite quarantine, our unquestionably qualified quorum has quashed our quasi-queasiness about quirky quantum quintessentials. Kiralee, Michelle, Kathy, thank you so much for entertaining and educating us tonight and shining a light on a world that is as weird as it is wonderful. You've provided us with a glimpse into Australian quantum science and engineering and given us a cause for a lot of optimism with the national opportunity that a future quantum industry presents. And it's been an incredibly uplifting session. So as a token of our appreciation, there are 3 little packets that will be tunneling their way from ANSTO to each of you via Australia Post. On behalf of the Australian Institute of Physics, our sincere gratitude goes to our partner organisations for another successful joint event. As Adi mentioned, they are the Royal Australian Chemical Institute, the Royal Society of New South Wales, and ANSTO, which isn't royal, but it is perfect nonetheless. A special note of thanks to you, Adi, for magnificent hosting tonight. And also, not at the front, but working tirelessly in the background is Mark, ensuring that the technology was faultless this evening. So thank you very much. You may know that this event is traditionally held physically at the ANSTO Discovery Centre. We've been holding it there for quite a few years now. Obviously, we can't do that tonight. And I'd really like to congratulate Fred Osman and Rod Dowler for responding to the challenges presented by the current restrictions and creating this engaging virtual event, which has actually reached more than 10 times as many people as the normal event would. And on that bombshell, back to you, Adi.
Great. I think the last message from me is that whatever we do with our science, let's make the world a fairer place, let's make it a safer place, and let's make it a happier place. And I think we've had 3 people and the wonderful support of all of these organizations that makes us have a glimpse that that could be possible. Thank you.
Thank you. Thanks, Adi.
Thank you.
Bye-bye.
Bye.
Bye, everyone.